Section 9.5 is going to look at the dot product of two vectors and what it means, and then we're also going to find the angle between two vectors, right? So not just the angle between a vector and the x-axis, what we called alpha. We're actually going to take two vectors heading in different directions and be able to find the angle in between them, right? So to start this off, I wrote two vectors, v and w, okay, in their ij component notation. So a sub 1i plus b sub 1j. And then w is going to be a sub 2i plus b sub 2j. But here it is in the other vector form, a sub 1 comma b sub 1, okay, and vector a sub 2 comma b sub 2. So when we calculate the dot product, the formula is we're going to multiply the a components together. So we're going to do a sub 1 times a sub 2. We're going to multiply the b components together, and then we're going to add them to each other. All right, so multiply the a components together, add to it the b components added together. So I want you to note, all right, that this is going to be a scalar. This is not going to be a vector. All right, it's going to be a scalar, right? Just a number. Dot product is a scalar. All right. So I'm going to calculate a few dot products, and then I'm going to do my best to show you what the dot product represents. All right. So let's say we have a vector v 2i minus 3j and a vector w 5i plus 3j. Okay. So if I wanted to do the dot product between v and w, we're going to take the a components and multiply them together. So 2 times 5. And then add to it the j components multiplied together. So negative 3 times 3, if you will. So we're going to get 10 plus a negative 9, which gives us a dot product of 1. All right. Now, what happens if we do w dot v? Okay. Mathematically, we're just doing the same mathematics, right? The first one's going to have 5 times 2 multiplied together. The second one's going to do 3 times negative 3. So because multiplication is commutative and so is addition, we're always going to get the same result. Okay, so we're going to get 1 here. Right. Now, one more. You can do a dot product of a vector on itself. Okay, so if I were to do v dot v, I'm going to multiply 2 times 2 plus negative 3 times negative 3. Right. So this is going to be 4 plus 9, which is 13. All right. All right, so what does a dot product represent? Right, I'm going to graph, right, these dot products here. Or I mean, not the dot products. I'm going to graph these vectors. So vector v, to the right 2 and down 3. So here's the head of the vector. Okay, so here's the vector v. Now, w is to the right 5 and up 3. Here's w. All right, the best explanation that I've found of what a dot product represents is something called a projection, okay, or a shadow, if you will. All right, so I'm going to rotate this paper to where the V is kind of parallel here, right? And imagine that there's a light shining straight down. So that W is casting a shadow onto V. So we have a light source up here, right? And so the shadow is going to cover just this much of the vector. Well, it turns out the projection of W onto V is only 1 unit long, right? So if there was a light source directly above, okay, and there was a shadow below it, the length here would be 1. Now, if I were to do the same thing with the projection of V on W, so again, I'm going to kind of make W here, I know it's upside down, but make this completely horizontal, and then make a light be at a 90-degree angle here. The projection of V onto W is also 1 unit long, right? So it's like the shadow, right? The projection of V onto W. That's the best explanation I can come up with. Now, this projection of V onto V is, if we had, this was 2 and this is 3, right? What would that be? I think that would be rad 13, right? The distance is rad 13. But if we projected it on itself, why it doubles that, I'm actually not too sure, okay? How we could project a vector onto itself and get, the distance squared, I'm not too sure. 2 squared plus 3 squared is c squared. Yeah, so c squared is 13, and I'm not exactly sure how this works out, but the projection does seem to help, okay, the shadow on one vector from another. All right, so let's also look at finding the angle between 2 vectors. Actually, you know what? Shoot. Before I move on, okay, I would like to talk about what if 2 vectors are perpendicular. Right. So what if I had a vector going straight up and a vector going straight down? Okay, what would happen if I had a light source here and I projected this vertical vector onto the horizontal? They would have 0 distance, right? So if the dot product is 0, then the vectors are perpendicular. And the book is not going to use the word perpendicular. The book is going to use the word orthogonal. And orthogonal just means perpendicular, right? It's the same word, okay, same meaning, right? So if the dot product is 0, right? If the one vector doesn't cast any shadow on the other one whatsoever, that means it's straight up and down, okay? So if the dot product is 0, then the 2 vectors are perpendicular. So if the 2 vectors are perpendicular, what's the angle in between them? Okay, so then angle between the 2 vectors, 90 degrees, right? It's a right angle, okay? All right, so let's find the angle between 2 vectors. So we have a formula for that, and the formula goes like so. Cosine of theta is the dot product on top divided by the magnitude of u times the magnitude of v. All right, so I'm doing a dot for the dot product, but these are just multiplied together because they're written next to each other. I don't want to do a dot product, okay, of those 2. I can't do a dot product because this is a scalar and a scalar. You can only dot product vectors, all right? So theta here is the angle between u and v. It's the angle between the 2 vectors. Excuse me again. So a couple things, all right? So if the angle between the two vectors is 0 or pi, okay, if theta is 0 or pi when we go to calculate it, right? If the angle between the two vectors is 0, they're right on top of each other. If the angle between the two vectors is pi, then they're heading in opposite directions, right? But what we say is that the two vectors are parallel. And, like on the other side, okay, if the dot product is 0, that means that the angle between the shadow is 0, and so the angle between the two is 90 degrees. Right? And when the dot product is 0, we know the two vectors are perpendicular. Or orthogonal. All right, so let's go ahead and work through two problems here, two examples. So I'm going to give you V is 2I plus J, and W is I minus 2J. And we have three parts, okay? We want to find the dot product. We want to find the angle between V and W. And then we want to state whether they're parallel, perpendicular, or neither. Right? Are they parallel? Are they orthogonal? Or are they neither? All right? So A, let's go ahead and find the dot product. V dot W. So we're going to take the I components and multiply them together. So 2 times 1. And add to that the J components multiplied together. 1 times negative 2. Right? So 2 times 1 is 2. 1 times negative 2 is negative 2. So if I add 2 and negative 2, I get a dot product of 0. So already, okay, we know that if the dot product is 0, right, that means V is not casting any shadow on W, and vice versa. That means they're orthogonal, right? So I already kind of know the answer to C here. But I would like, and I actually already kind of know the answer to B, because I know they're orthogonal as well. But I would like to show you the work here. So find the angle between V and W. So we're going to do cosine of theta is equal to the dot product divided by the magnitude of U times the magnitude of V. All right? So U dot V, okay, is 0. The magnitude of U is the square root of 2 squared plus 1 squared. And then the magnitude of W is 1 squared plus negative 2 squared, right? That's how we find magnitude. Now, this magnitude isn't so necessary because 0 divided by anything is 0, right? So this magnitude is rad 5. So is this. Let me go ahead and keep going, though. I'm going to get 0 over rad 5 times rad 5, which is 0 over 5, right? So what's cosine? I have cosine theta equals 0, right? So if I were to cosine inverse this, or what angle has a cosine of 0, right? So if I were to cosine inverse this, the calculator is going to give me 90 degrees, right? And if the angle between the two vectors is 90 degrees, then they're orthogonal. So two ways here, right? The dot product is 0, which forces the angle between the two vectors to be 90. And so the answer to C here is the vectors are orthogonal. It's our new word. All right. All right, let's do the same thing. Okay, same directions, A, B, and C, but two new vectors. Let's do V is 3I minus 4J, and W is 9I minus 12J. Okay. So first, let's find the dot product. And so we're going to do the I components multiplied together plus the J components multiplied together. And so we're going to get 27 plus 36 is, not 36, oh my, 48, which is a dot product of 75, okay? So then let's find the angle between them, all right? So cosine theta is V dot W divided by the magnitude of V times the magnitude of W. So V dot W is 75, right? What's the magnitude of V? Okay. We're going to get 3 squared plus negative 4 squared. And then the magnitude of W, 9 squared plus negative 12 squared. So kind of big numbers here. Alright, so the square root of 3 squared plus 4 squared is 5. And then the square root of 9 squared plus 12 squared is 15. Right? And 5 times 15 is 75. So we're getting 75 divided by 75 here. So really cosine of theta is 1, right? So we can cosine inverse this, but really what angle does cosine have a value of 1 on, right? Isn't that 0 degrees? Or even, 0 degrees. Cosine is 1, okay? And so theta here is 0 degrees. Well, ding, 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 that gives you a warning, right, that it's either parallel or perpendicular. So if theta is 0 degrees up top here, then we know that the angle between them is 0 degrees, which means they're parallel, okay? So on C, V and W, not U, V and W are parallel. Okay. So I hope that makes sense, and I hope you have a blessed day.